Good morning, dear student. In today's lecture, we discuss the relationship between magnetic susceptibility and temperature. That is, it is denoted by symbol chi m. Okay, so the relationship between magnetic susceptibility and temperature. Okay, let us discuss. So in previous lecture, we already discussed the wave theory, that is domain theory for ferromagnetic materials. According to this domain theory, there is a two postulates. One is domain postulates, domain, and second is the internal molecular field or exchange coupling interaction. So let us discuss the relationship. So whatever the internal molecular field or the internal exchange interaction is given, so the first point is that the internal molecular field, so whatever the interaction within the atoms, within the domains, or we can consider the internal molecular field is given as the internal molecular field is given as, or whatever the interaction within the atoms of domain is given as bm, which is equal to mu 0 into gamma into m. So let us consider this is as equation 1. So in this equation, mu 0 is your permeability, this gamma is your Weiss constant, and this m is nothing but your spontaneous magnetization. So this is the equation in absence of external magnetic field. So whatever the interaction within the domain, that is within the atoms of domain, it will give this equation, that is internal molecular field is given as mu 0 gamma m, where mu 0 is permeability, gamma is Weiss constant, m is a spontaneous magnetization. Again, second, that is the external magnetic field is applied. So second, that when the external magnetic field is applied and the external magnetic field is given as the b vector, it is your external magnetic field. So external magnetic field is applied, so b vector, which is equal to external magnetic field, b vector, which is equal to mu 0 into h, mu 0 into h, and mu 0 is nothing but your permeability, and h is your magnetizing intensity or magnetizing strength, or the external magnetic field strength, magnetizing intensity or the strength of external magnetic field. So this is the two equation. One, in absence of external magnetic field, it is due to the internal molecular field or exchange interaction, and second is due to the external by the application of external magnetic field, that is b vector, which is equal to mu 0 h, where h is your magnetic intensity, magnetizing intensity. Let us consider this is as equation second. The effective field is given by, then the effective field the effective field is given by b effective, which is equal to bm, that is internal molecular field. So whatever the internal molecular field due to the exchange interaction plus b external external magnetic field is applied. So it is a combination. So b effective, so overall magnetic field is nothing but bm plus b external. So what is the value of bm? So bm, we know bm is your mu 0 gamma m, mu 0 gamma mu 0 into gamma into m, plus what is the value of b external is here, mu 0 into h. So from this equation we can take a common, that is mu 0 is common from these two equation. So what you get, B effective, which is equal to mu 0, uh, take outside, and what is remaining, that is the remaining is what, H plus gamma into M, H plus gamma into M. So mu 0 is common, and what is remaining, the magnetizing intensity gamma is a base constant, and M is your spontaneous magnetization. So let us consider this is our equation 3. So we get B effective, that is mu 0 in bracket H plus gamma into M. So let's discuss the next point, where uh, M is nothing but your spontaneous magnetization, and M, the another M we already discussed in previous lecture, that is uh, what is this M or magnetization, magnetic moment per unit volume. So M is given as, the magnetization is also given as magnetic moment, magnetic moment per unit volume. So we know this definition. Magnetization is nothing but magnetic moment per unit volume. And for paramagnetic material, the magnetic moment for paramagnetic material, the magnetization is given as N, which is equal to N pm square, N which is equal to N pm square, N pm square into B upon thrice kt. So the magnetic moment per unit volume. So M is nothing but, it is not magnetization, it is magnetic moment per unit volume. So keep in mind. So I will make mistake here. So M, no doubt, so small m represent the spontaneous magnetization, but we consider here M, that is magnetic moment per unit volume, and the magnetic moment per unit volume, magnetic moment per unit volume for paramagnetic material, magnetic moment per unit volume for paramagnetic material is given as M, which is equal to N pm square into B upon thrice kt. So B is your external field, okay, M is your magnetic moment, and then K and T is your constant, N is nothing but your number of atoms, and this Pm is nothing but your magnetic moment. Okay, this Pm is nothing but your magnetic moment. So in this case, this is B, this B is nothing but your B effective. So overall magnetic field, overall field we can consider B is your field, then M is nothing but your magnetic moment, magnetic moment, that is Pm square, we consider it is a magnetic moment, and N is nothing but the number of atoms within the material. M is nothing but the number of atoms within the material, and this equation for paramagnetic material. So whatever the magnetic moment per unit volume in paramagnetic material, it is given as M, which is equal to N pm square B upon thrice kt, N pm square B upon thrice kt. For diamagnetic material, B is equal to B effective. So for diamagnetic material, for diamagnetic material, B is equal to B effective, and therefore we substitute here, we write this is nothing but your external field, external field. So we take the help of this paramagnetic and diamagnetic material to derive the relationship between magnetic susceptibility and temperature for ferromagnetic material. So initially we derive the equation, that is B effective, which is equal to mu 0 in bracket H plus gamma M. Again, the second point is that M is nothing but your magnetic moment per unit volume. The magnetic moment per unit volume for paramagnetic material, it is given as N into Pm square into B upon thrice kt, where N is nothing but your number of atoms, Pm square is nothing but your magnetic moment, B is your external field, and K and T is constant. For diamagnetic material, B is equal to B effective. So whatever the external magnetic field is nothing but your B effective, and using equation 3 and 4, So using equation 3 and 4, so using equation 3 and 4 we get, so this is equation also already we discussed up to be effective is our equation 3. So this is equation 4. So this is equation 4. So using equation 3 and 4, or in other word we can say that substitute the value of B effective of from equation 3 into equation 4 we get. So what you get here, so let us substitute this value, that is B effective, which is equal to mu 0 H plus gamma m. So this is your equation 3. So let us substitute this value for diamagnetic material. B is equal to B effective, therefore this value is substituted into this equation. So what you get here, so let us discuss it. So substitute the value of B is equal to B effective. So B effective value is known, so we get here m, which is equal to, that is magnetic moment per unit volume, is equal to n pm square upon thrice kt, and instead of B we can write this as mu 0 into in bracket H plus gamma m. So we get this equation. So let us solve it. So we can write this as m thrice, or we can write thrice ktm. So this thrice kt get multiply here, so m thrice ktm, which is equal to n pm square mu 0 into H plus n pm square mu 0 into gamma m. So after multiplication we get this equation, that is n pm square mu 0 into H plus n pm square mu 0 into gamma m, and then we can write this is the equation, that is thrice so we can write this is thrice ktm. So this is your thrice ktm is there. So thrice ktm minus, so we have to shift these terms into this left hand side, so it becomes minus. So what you get, thrice ktm minus n pm square mu 0 gamma m, which is equal to n pm square mu 0 into H. So from this equation we take m as a common. So what you get here, thrice kt, okay, minus n pm square mu 0 into gamma, and the m have to take outside the bracket. So m is common, and here what you get here, n pm square mu 0 H, and from this equation we can write m, which is equal to n pm square mu 0 H upon thrice kt minus n pm square mu 0 gamma mu 0 gamma. So this is the equation we get for m, that is magnetic moment per unit volume. So we get this equation. So let us go further, and then we can write the equation for m by H. So you have to transfer this H from this side, so you can write, so what you get, so m by H is nothing but your magnetic susceptibility. M by H is nothing but your magnetic susceptibility. So what you get here, n pm square mu 0 upon thrice kt minus n pm square mu 0 into gamma. So we get this equation, that is, and the m by is nothing but your magnetic susceptibility. Magnetic susceptibility. Magnetic susceptibility, and it is having a symbol chi m. So we can write here chi m, which is equal to we get this equation, that is whatever the equation we can write here, same is here, chi m, which is equal to the same equation, that is n pm square mu 0 upon thrice kt minus n pm square mu 0 into gamma, mu 0 into gamma, same equation, but instead of m by h we can write magnetic susceptibility. So for our convenient, uh, we slightly modify this equation by dividing, uh, if you take 3k as a common. Okay, so for our convenient we making slightly a modification in this equation. So if you take 3k as a common, so for getting 3k as a common, you have to divide the 3k, you can divide it the denominator by 3k. So if you take 3k as a common, for getting 3k as a common, you have to divide this denominator by 3k. So what you get, x by m or chi by m. Okay, for our convenient we consider it is x. Okay, chi by m, which is equal to, so what you get here, we take thrice k as a common. So to get thrice k as a common, you have to divide this denominator by thrice k. So what you get, n pm square mu 0 upon thrice k. Okay, thrice k t minus n pm square mu 0 into gamma upon thrice k, upon thrice k. So we get this equation. So for our convenient, you have to take 3k as a common. For getting 3k as a common, you have to divide the denominator by 3k, and denominator, whatever the term in denominator of denominator is transfer into numerator. So whatever the term in denominator of denominator, okay, the term which is divided, or we can say that whatever the term in denominator, okay, below the denominator is transferred into numerator. So those students having mathematics, they understand it. So just this 3k is just transfer to the numerator, transfer to numerator. So we can write this equation as, that is x by m or chi by m, which is equal to n pm square, n pm square, or not, you only understand this up to this. That is, we take 3k as a common. For getting 3k as a common, you have to divide the denominator by 3k, and the whole the other terms is same. Okay, so what you get here, n pm square mu 0 upon thrice k. So this term is remain as it is. Okay, n pm square mu 0 upon thrice k. Okay, and we can write this as t minus, in bracket, n pm square mu 0 into gamma upon thrice k. Okay, so keep in mind what you get. Okay, so first, for taking the 3k as a common, you have to divide this denominator term by thrice k, and then we get this equation, that is n pm square mu 0, n pm square mu 0 upon thrice k divided by t minus n pm square mu 0 upon thrice k into gamma. And we can write this equation, that is chi by m, which is equal to c upon t minus c into gamma. So what is the c? C is nothing but your Curie constant. So whatever the term, that is n pm square mu 0 upon thrice k in denominator and numerator, it is replaced by the c, and c is nothing but your Curie constant. C is nothing but your Curie constant. So we get this equation, that is x chi by m, which is equal to c upon t minus c gamma. So c upon t minus C gamma. So what is your C? C is nothing but your Curie constant. The whole term is nothing but your Curie constant. So what you get here? So finally, what you get here? So we can write this as chi by m. This equation we can write as C upon T minus T prime. T minus T prime, where T prime is nothing but your C into gamma, which is equal to a constant. So you have to slightly modify this equation, that is chi by m, which is equal to C upon T minus T prime, where T prime is nothing but your C into gamma. It is just multiplication of this C, that is Curie constant, into the West constant T prime. And the condition, that is when T is very greater than T prime, when T is very greater than T prime, then T prime is negligible, and we get this, that is X, that is chi by m, which is equal to C by T, which is equal to C by T. What this equation tell us? So this is the relationship between magnetic susceptibility and the temperature. That what this equation tell us, that is the magnetic susceptibility is inversely proportional to the temperature. And many times this equation is asked in exam to prove the relationship between the magnetic susceptibility and temperature, or derive the equation for magnetic susceptibility, derive the relationship between magnetic susceptibility and temperature. So you should understand the relationship between this magnetic susceptibility and temperature, that is they are inversely related, means as temperature is increases, the magnetic susceptibility is decreases. As temperature is decreases, the magnetic susceptibility is increases. So one is decreases, one is increases. So this is all about the relationship between magnetic susceptibility and temperature. In the next lecture, we'll discuss the remaining points of this section. Thank you.